Thank you very much for the invitation to give this seminar. I'd like to speak on on free omega continuous and regular ordered algebras. This is some joint work with Zoltan Ashik from Szeged. Zoltan was a dear friend and colleague. I didn't want to do that. There's his picture. He died, unfortunately, a few years ago. He and I started doing this work at a LICS conference in New Orleans, I think it was, back in maybe 2014. And we got together, talked about some ideas, and came up with a draft. And then he tragically passed away quite suddenly. And so I thought in his honor, I would put this paper together, this work together, and submit it someplace. But I believe this is his last publication. It was just recently published. Zoltan and I had I guess you could call it a love-hate relationship. It was more love than hate, but I admired him greatly. He was a consummate scholar, and I admired him. I admired his work. We did have quite a bit of competition going because we were both working on systems that purported to capture the notion of computation at a basic propositional level. He was, of course, the proponent of his work with Steve Bloom on iteration theories, and I came from the point of view of Kleene algebra, both of which were directed toward the same goals, and so we're constantly talking to each other and competing with each other about what was the best way to do things. But I miss him greatly, and he was his work is monumental. I think if you look at some of his work on iteration theories with Steve Bloom, it's some of the best work in the area. So this talk is dedicated to his memory. Okay, what I want to talk about is varieties of ordered algebras, and these are objects that come up constantly in computer science. They are all over the place. Order is, of course, very fundamental in a lot of models that are used to model computation. Here's a list of some of them: closed semi-rings and quantiles, star continuous Kleene algebras with tests, context-free languages, lots of examples from formal language theory, of course. Some rather unusual languages that I had the pleasure of rediscovering, or I didn't rediscover them, but got a chance to dig out some old literature and relearn them. Iteration theories, which is the work of Zoltan and Steve Bloom, and some early work on higher order recursion schemes, and of course, partial orders, complete partial orders, and Scott domains. So the order is very important in all of these. There are many properties of interest that are expressed in terms of order. You can reduce a lot of things that you want to do in computer science to reasoning in ordered domains. Partial correctness is, of course, the statement of this is an implication. Preconditions imply some postcondition being true, and after executing a program, that's essentially a statement about the ordering of assertions. Program refinement, whether a program satisfies its specification. Abstract interpretation, many other examples of this. Now, it was really Zoltan's main thesis that to understand about such properties, you should study the free algebras. And the reason why free algebras are important is because they, if you accept the premise that the important properties, many of the important properties can be specified by equations or by inequalities in the ordered case, then the the equational theory or the inequational theory is captured in the theory of the free algebras. Okay, it gives you a concrete representation of that equational theory. Usually it's related to soundness and completeness of axioms and can often lead to decision procedures if you look at the co-algebraic aspects of this. In this talk, I want to talk about certain ordered sigma algebras with, and I want to say, syntactically restricted completeness and continuity properties. So these are ordered algebras that have completeness properties in the sense of least upper bounds being existing, suprema of ordered sets existing, but not necessarily all suprema, but only certain suprema. So that's what I mean by syntactically restricted. And I'll show exactly what I mean by a syntactic restriction that specifies which suprema exist and which don't exist. And I'm going to define a general class of these things and call them quasi-regular. The main result is a characterization of the free algebras of these quasi-regular systems in terms of submonads of the monad of sigma coterms. And I'll define all this stuff presently. By the way, I'd just like to say that if anybody has a question at any time, please feel free to jump in. You can just unmute and ask the question. Just grab my attention and I'll be happy to try to answer.
Or let me just ask one.
Yeah.
So sigma algebra in this context, what does it mean?
Sigma is going to be an algebraic signature consisting of some function symbols with various
arbitrary algebraic signature, something like that.
Yeah, algebraic signature, like signature of groups or monoids or something like that. And sigma is the collection, is a ranked alphabet, is a collection of such symbols. And I'll be forming the terms and the coterms, which are infinite terms over these. Okay, let's take an example to start off with. So here's Stephen Kleene, another one of my heroes, who invented finite automata and regular expressions. The algebraic theory of regular expressions is captured in the notion of Kleene algebra. Here is an axiomatization of Kleene algebra. Now, normally we take the idempotent semi-ring axioms, and you can make an inequality out of it, out of equality by this definition that defines P less than or equal to Q if P plus Q equals Q, and that becomes a partial order basically because of this idempotence axiom for plus. So idempotent semi-ring, which is the normal axioms of semi-ring plus idempotence, gives you a partially ordered set. And then for star, the star of a regular expression is axiomatized by these axioms. Now there's an alternative axiomatization that gives you something called star continuous Kleene algebras, which are Kleene algebras. So normally we take these this inequation and this implication, equational implication. So it's a finitary Horn axiomatization. But normally we take that as that's the standard axiomatization for Kleene algebra. But there's a little bit stronger axiomatization that's given by this axiom, which is called the star continuity condition. And it says that the element PQ star R is the supremum in the natural order, defined this way, of the set of objects of the form PQN, Q to the NR, where Q to the N is the nth power of Q under the multiplication operation of the semi-ring. Okay, so that's a stronger axiomatization. These axioms that I've crossed out here are actually consequences of this stronger thing. But this is infinitary. It's not, in order to talk about, so it's really, you can axiomatize it with a Horn formula, but there are infinitely many premises in this expression of supremum. Okay, so the star continuity is, as I say, it's stronger. It doesn't give you any more equations. Okay, so if I go back here, the the equational theory of Kleene algebras is fully axiomatized by these finitary axioms that I crossed out. And this infinitary axiom does not give you any more equations, but it does give you more Horn formulas. So it essentially says, this says that Q star is the supremum of this set, infinite set of Q to the n in the natural order. And including the P on the left and the R on the right here, says that multiplication is continuous in both arguments with respect to these suprema. So this is kind of a syntactically restricted form of, or specification of a set of suprema that exist. So not all suprema exist. So Kleene algebras are not, the supremum of any set is not assumed to exist, but these suprema do. So it's a syntactically restricted form of that. Now, all of the standard models that come up in real life are star continuous. So it may be a good argument for accepting this star continuity condition. The reason for taking the finitary axiomatization is that it's a little bit more tractable if you want to implement it in an automated deduction system. But mathematically, there's no reason, if you're only interested in the standard models, there's no reason not to assume this star continuity condition. Here are two standard interpretations that, of course, the granddaddy interpretation is the regular set of strings over a finite alphabet, where plus is interpreted as union of sets of strings, times is the set theoretic application, the set theoretic concatenation, which takes the set of all concatenations of strings. This is going to be generalized in the future, so bear this in mind. And then the star is this Kleene asteroid operation, which takes the supremum of powers. This is the free model of Kleene algebra. So that is the equational theory of this model is the same as the equational theory of all Kleene algebras, as axiomatized on the previous slide, which is also the equational theory of the star continuous Kleene algebras. Another class of models is given by relational models, where we interpret expressions as talking about binary relations, so subsets of set of ordered pairs on a set on a universe X, where again plus is interpreted as union, multiplication is relational composition defined this way, and star is the reflexive transitive closure of a relation. And one is the identity relation, 0 is the null relation. And the equational theory of these models is also the same as the equational theory of all Kleene algebras. Now, I mentioned that the star continuity condition asserts the existence of certain suprema. And you can see the form of the suprema that are asserted by the axiom, but there are actually more suprema that are implied to exist by this axiom. And let me explain this, because this is kind of an important thing to understand. That's a big part of what we're doing. So it says that if I look at all Kleene algebra expressions over the alphabet sigma, okay, so the regular expressions are, these are the regular, so-called regular expressions. And the standard interpretation, let's call it R, interprets each expression as a regular set. And this is the standard interpretation that interprets a symbol A in sigma as the set containing A. And then that's the sub-Kleene algebra of the Kleene algebra of all subsets of sigma star. Let's let K be any star continuous Kleene algebra. Then it's the case that certain suprema exist in K. that are implied by the star continuity condition. And it's expressed this way. So for any P, Q, and R expressions in regular expressions over sigma, the following holds in K. If I interpret in K, the interpretation of PQR in K is the supremum of all of the expressions PXR, where X is a string in the regular expression denoted by Q. So what that says is that if you take Q, the regular expression Q, and interpret it as a set of strings, that could be an infinite set, it's typically an infinite set, and look at the set of expressions of this form with P, X, and R, with X in the middle, one of those strings, that's potentially an infinite set, large infinite set of that I can interpret in the Kleene algebra K. So take any interpretation in K of these expressions, that gives me a set, and the supremum of that set exists. And that's implied by this special case of the star continuity condition. You can see that this is the special case for Q equal for the middle thing being something of the form Q star. Okay, so that's a large set of expressions that exist. All right, so this essentially says that, so the special case says that Q to the n, that infinite set has a supremum. This says that any regular expression, the set of X interpreted in K has a supremum, and that the P and R on the left and right assert the continuity of multiplication with respect to such suprema. Okay, so that's this green statement down below. So that is a primordial example of something that that I want to talk about in this talk, and that I'm going to generalize. I'm going to give a way of doing this quite generally. So this is the special case for Kleene algebra. Okay, any questions so far? Everybody with me? Okay, so let's go on to the general definition. So I want to look at ordered algebras in general. So let's let sigma, in this case, be a ranked alphabet. It's going to be, I'm going to consider sigma algebras, which are algebras that give an interpretation to each element of the ranked alphabet as functions of the appropriate arity on a set of, on a carrier. And I'll say that the sigma algebra is ordered if it's partially ordered by some, if it has a partial order defined on it and a least element that I'm going to call bottom, and that the algebraic operations are assumed to be monotone with respect to this order. So that just says that if I have a function symbol of arity n and all of its arguments are ordered in this way, then f applied to the a's is less than equal to f applied to the b's. You can generalize this by assuming contravariance in some of the arguments, but I'm not going to do that. Let's just assume covariance in terms of all the arguments. Okay, so that gives you an algebraic structure, and then I'm going to make a category out of it by defining the morphisms to be any strict monotone map that commutes with the algebraic operations. So it has to be monotone, which is this axiom here. If A is less than B, then H applied to A has to be less than or equal to H applied to B. It has to be strict, which means I map bottoms to bottoms, and it has to be a morphism in the usual sense, which means it commutes with the algebraic operations, commutes with the structure map of the algebra. So that's an ordered algebra. The term algebras can be made into an ordered algebra. So usually in term algebras, you just form the set of terms over the signature. Here I'm going to form the set of terms, but I'm going to allow some terms to be missing. So I'm going to be able to delete some subterms, just get rid of them. And that's the same thing as having the empty term. In this interpretation, the free ordered sigma algebra is just the set of partial terms where I just, finite partial terms where I just allow some elements to be dropped out. And that element being dropped out just means that you can think of it as this bottom being there. So bottom in this model is the empty term. Okay, so partial here, a partial subterm means some terms may be missing, and the missing ones are equivalent to bottom. So I don't have an explicit symbol for bottom. It's just, it's not, the term is not there. So bottom is really is represented by the empty term. Okay, so this is the free ordered algebra, and by that I mean whenever I have an ordered algebra, any function, any set function from the generators x into the carrier of A extends uniquely to a morphism from the free term. Okay, so that's that. Now, an ordered algebra is omega continuous if it's omega complete, which means any non-empty countable directed set has a supremum. This is sort of a very strong completeness property, very strong completeness and continuity property. So it has to be omega complete, which means any countable set, directed set has a supremum, and the operations have to be continuous with respect to those suprema. So that just says that f applied to a set of an n-ary function f applied to a list of suprema has to be give you the same thing as the supremum of f applied to the elements of the chains or directed set. Okay, and a morphism of this category, omega continuous algebras, is an omega continuous ordered algebra morphism. So it's a morphism that preserves suprema in this sense. Okay, so this is a subcategory of the ordered algebras, omega continuous ordered algebras. Now there are free omega continuous algebras. So in the same sense they were free ordered algebras, there are free omega continuous ones, and these are given by the omega continuous coterms, I'm going to call them, partial coterms, which are like terms except they're infinite. They can be infinite. So here's an example of two infinite partial terms. They're partial in the same sense that the finite terms were. You can leave subterms out, which makes them ordered. And these are two examples of two infinite terms. This is a regular term, and this is a non-regular term, but also with some, you can see there's some pattern here that's being duplicated as you go down the term. So this is a so-called algebraic term. So there is a free omega continuous sigma algebra freely generated by X. That's the set of coterms, a set of partial coterms. Okay. So formally, if you want to formalize this, the best way to do it is as a labeled tree. So I'm just going to label take labelings of sequences of integers. It's a partial labeling with either a variable or an element of the signature, such that the domain is prefix closed, and then this property here that says that if I have a string of, if I have a path in the tree that's labeled with some element, if it's in the domain, then its predecessor has to be labeled with an n-ary function symbol, and I has to be less than n, has to be between 0 and n-1. Okay, so this is the formal definition of a so-called coterm. And when A is omega continuous, any set function extends to a morphism, to an omega continuous morphism from the set of infinite terms to A. Now, in some sense, the two models that I've given already, the two types of terms, so the finite terms and the partial terms and the partial coterms are the extremes. They're like the least set of terms you might want to take and the greatest set of terms you might want to take in terms of completeness. Now these can be equipped with equations if you like, so you can get varieties by allowing equations, or inequalities we'll call them. So usually varieties in equational logic are defined in terms of equations. Varieties in inequational logic are defined in terms of inequations or inequalities like this. So if I take a fixed set of formal inequalities, I can look at the variety of ordered algebras that satisfy those inequalities and the variety of omega continuous algebras that satisfy those inequalities, which is going to be a subvariety of the variety of all ordered algebras. So I'll say that an ordered algebra belongs to the variety if the interpretation of any term, if those stand in the relation anytime the axiom t less than or equal to t prime is in the set of axioms E that you're given. So this is the variety determined by a set of formal inequalities E. And then V sub omega, the omega continuous ones, is just the subvariety consisting of all the omega continuous ones. Now it's known, this is what was known up to the point at which Zoltan and I began our work, that there are two extremes. There are known to be free algebras in V. These are the free ordered algebras, and the omega continuous ones, which is the other extreme. So that's due to Bloom and Gassarian in around late 70s, early 80s. Okay, so there are these free algebras on generators X. And the free algebra F sub X is the subalgebra of F omega X generated by X. Okay, so, and they gave a characterization of how you can get the omega continuous one, or you can get an omega continuous one from an ordinary one by completing it by doing the completion by omega ideals. So it's a nice characterization of the free models in this case. So what exactly does this mean? What is an omega ideal? So take an ordered algebra that may or may not be complete, may not be omega complete, but I'll take a set C and a subset of A that satisfies the following properties. It's got to be directed. So that means that for any two elements, there's an element that dominates both of those elements in C. So it's kind of closed upward under it's directed in the usual sense. And it's downward closed. Anytime you have an element less than another element in C, then it is in C. So C is equal to the downward closure. And finally, it has to be countably generated. So there's a countable directed set that generates C. Okay. And when those three properties hold, that set is called an omega ideal. And if I take the set of omega ideals of a model, you can embed the model into the set of omega ideals. What you take, every element goes to the downward closure of that element. But the set of omega ideals forms is an omega complete partially ordered set. You can define the operations on it. You can define the operations on the omega ideals by the application of an n-ary function f to a set of omega ideals is just the set of f applied to the elements of the ideals. Now you saw this before with the way we formed the concatenation of two regular sets. It's the same thing going on here, except more generally. And this is there's an embedding of the original algebra A into the set of ideals by just take A to its downward closure. And it turns out that I omega A is the free completion of A to an omega continuous algebra. And in particular, for these models without any equations, if I don't take any equations at all, then the class of the family of coterms, of partial coterms, is isomorphic to the ideal completion of the finite terms. Okay, so that was what was known. So I'm going to generalize this, and to generalize this, I want to make some observations that were not clear from the earlier work. There was no notion of monads in that earlier work, but that's really what's going on. So we can define these monads which consist of a set or an endofunctor on set, and then two natural transformations, mu and eta, that work in the usual way that monads work. Applied to terms and coterms, well, there's the term monad, which you may be familiar with. The coterm monad works exactly the same way. So eta takes an element x and just makes a singleton term the same way. So it works the same way as in terms. For coterms, I take a coterm of coterms and just flatten it to a coterm. So it's a flattening operation, the same way that, say, lists of lists get flattened to lists. Okay, so you can define this in general on the coterms, this monad, and then the term monad is just a submonad of CT with a suitably restricted domain, with domain restricted to the finite terms. Okay, but this is the most general monad I want to take, and this is the smallest. Now there's stuff in between, and that's where we're going to get back to that in a minute. Just let me say one more thing. So when you have a monad, you have a class of algebras for that monad. And these are the so-called Eilenberg-Moore algebras, which are equivalent to the usual formulation of algebras, but they work on monads instead of just arbitrary signatures. So it's just a pair consisting of a set and then an evaluation morphism that tells you how to interpret the elements of the elements of the signature, and it has to satisfy these commutative properties. Okay, so this is like a generalization of what I've been saying so far in terms of interpretation in terms of algebras. So you can formulate all this in these terms, and the ordered algebras. The ordered algebras and omega continuous ordered algebras are the Eilenberg-Moore algebras for the partial term monad and the partial coterm monad. And the free algebras are the finite partial terms and the finite partial coterms. So these are without any equations. And then you can add equations if you like, and I'll be doing that later. Okay, so FT and CT, these are the two extremes, but there is stuff in the middle. And this is how I want to define my limited completeness and continuity condition. I want to define it in terms of a monad delta that sits in between CT and FT. So what was known so far up to this point was this theory of varieties of ordered algebras and omega continuous ordered algebras that correspond to FT and CT respectively. But I would like to put stuff in the middle. So let's suppose that I have some monad that satisfies this relation in between. And the monad operations will be just inherited from CT in the same way that FT did. Okay. So I'm going to call the term algebras that are defined in terms of this submonad a quasi-regular family. So the regular sets will be an example. The context-free languages will be an example. There will be a bunch of examples. A lot of the stuff that I mentioned at the beginning of the talk will be examples of this. So I'm going to define the algebras that are defined in terms of delta, and they will have completeness properties in the sense that certain suprema of certain sets will exist, and the suprema that are assumed to exist will be defined by this monad delta, or will be defined by the coterms that are in delta, which is a submonad of the set of all of these things. Okay, so I'm going to use delta to be a kind of syntactic representation of what suprema exist. So let's see how this works. So the two extremal examples, as I mentioned, are CT, this is the biggest one, CTX, and FTX, that's the smallest one. They're the maximum and minimum quasi-regular families. I'm sorry, I can't hear. Try again.
Okay, it's okay.
I'm sorry, I didn't get that.
Yeah, okay.
Can you say again what you're asking?
No, somebody else is talking to me.
Oh, I see. I'm sorry. Okay, so I should just go on.
I'm sorry as well.
That's not a question.
Just go on. So that was
okay. Okay, sorry. I thought
yes.
thought that might have been a question. Okay.
Mm-hmm.
So these are the two extremal examples: the coterms and the finite, infinite partial terms and the finite partial terms. But there's stuff in the middle. These are the maximum and minimal quasi-regular families. Other quasi-regular families are regular and algebraic trees, regular or rational trees of order n, and union of n regular trees, which were studied by Gallier and other Courcelle. And there are other examples too, which I'll get to at the end. So I'll show you a bunch of examples at the end. Here's an example of a regular tree. So this is so the definition of a regular tree is a tree, it's an infinite tree that, an infinite labeled tree that has only finitely many subtrees up to isomorphism, okay? And that's the same as saying that I can represent the tree kind of co-algebraically by this finite co-algebra that if you unwrapped it would expand into this infinite tree if you unwrap this all the way. So you can have like a finite tree with loops in it, but if you unwrap it, you get this infinite thing. Okay, here's some algebraic trees. These are kind of fun. So these are trees that you can see have some kind of pattern going down, but they have infinitely many isomorphic subtrees. So there's no finite representation of these, but there is kind of a finite representation in the sense that I can describe in a finite way by some kind of context-free grammar how these trees are generated. And I'll get to this at the end. I'll show you how to do this at the end. Okay, so this is a larger example of a class of a delta class that sits inside the class of all infinite coterms. So we can define, once we have delta, this submonad, we can define the delta regular algebras. So here's the definition. It's rather long, but I'll go through it briefly. So if you give me two coterms, T1 and T2, I'm going to say T1 is way less than T2 if T1 is finite and if T1 is less than or equal to T2 in the usual sense. So T1 is obtained from T2 by, in the sense of coterms, it just means T1 is obtained from T2 by deleting some subterms. That's all it means. And I'll say that T1 is way less than T2 if it's, in addition, it's finite. Okay, so T1 is way less than T2 if T1 is finite and less than or equal to T2. And if I take an ordered sigma algebra with a structure map, FT going from FTA to A, this is a Eilenberg-Moore algebra for the finite term monad. I'm going to call B subset of A delta set if there is a coterm in delta such that B is the set of finite terms that are obtained from the big term t by deleting enough elements to make S finite. So take all of the finite, so it's like S is, the set B is a set of finite approximants to t. By taking the term t and then deleting enough elements to make S finite. And take all of the terms S, the finite terms obtained in that way. And now take all those terms and interpret them in the algebra A by the structure map beta. Okay, so that is a set of terms in beta that in A that I will call a delta set when it can be obtained in this way from a term t in delta. And that defines a set that I would like to have a supremum. And I'm going to define a delta algebra. I'm going to define an algebra delta regular if all of those suprema exist that are specified this way. All right. So I'm taking a coterm t, a big term in delta, has to be in delta. Take all the finite approximants of that term, interpret all those finite approximants in the set A, and then I would like the supremum of that set to exist. And I will call A delta regular if that happens. If the suprema exist, oh, and by the way, they have to be also preserved by the algebraic operations. Okay. So if that happens, then I can extend, if I have a delta regular algebra, then I can extend beta to give me a value, give me a supremum of all those things by defining beta of t for the coterm t to be the supremum of that set. So I have kind of a syntactic representation of this supremum. So it's like the star. The star operation in Kleene algebra gives me kind of a syntactic way of talking about these suprema. Okay. Supremum exists by the assumption that A is delta regular. Then with the extended structure map, beta is an Eilenberg-Moore algebra for the monad delta. Okay, so this is, so the motto of what I just did is that every delta regular algebra can be extended to a delta algebra, an Eilenberg-Moore algebra for delta. The extension is unique, and it gives me a syntax for supremum of delta sets. Okay, and a morphism of these things, so I can get a category out of it by defining morphisms to be the morphisms of the ordered sets with bottom that commute with the structure map. Okay.
Okay.
And delta algebra morphisms are delta continuous. That's what this theorem says. So here's some examples. If delta is just ft, then a delta algebra is just an ordered sigma algebra. If delta is ct, then I get the omega continuous algebras. If delta is the collection of regular trees, then I get an ordered regular algebra as studied by Turin and back in the late 70s, although he did not formulate it in this form that I've just done. If delta is the set of regular trees of order n, then I get a regular algebra, an n-regular algebra, a la Gallier. Now, here's the main result, and it's sort of a characterization of the free the free delta continuous algebras with inequalities E, in the same sense that was done previously for omega continuous algebras and just ordered algebras back in the late 70s and early 80s by Gassarian and Bloom. So if I take a variety of ordered algebras defined by a set of inequalities, and the omega continuous ones is a subvariety, now take the delta ones, which fit in between, then the free ordered algebra on generators X, that's Fx. F omega is the free omega continuous algebras, and F delta is the subalgebra of the omega continuous ones, denoted by the delta coterms in the way that I described earlier. And the free delta algebra is the completion of fx by delta ideals. So that is the main characterization of the free algebras. That's the main theorem of the paper. Okay, let's go on to some examples because this is more fun. I don't want to bore you with the technicalities of the main theorem because it's fun to look at, more fun to look at pictures. Okay, so here's some examples. The free omega continuous semi-ring, if I take the signature of semi-rings on generators X, that's the semi-ring of power series with countable support and coefficients in the natural numbers with infinity. Okay. The free regular semi-ring is the semi-ring of algebraic elements of that. So that's the semi-ring that is specified by algebraic, by the algebraic terms, algebraic coterms. The free omega continuous semi-ring is the semi-ring of at most countably infinite languages in X star. X is not required to be countable here in this definition. The omega continuous idempotent semi-rings are the same as the closed semi-rings used in the study of shortest path algorithms. There were a few errors in the axiomatization that was given. There's given in most of the literature on this. Okay, the free star continuous Kleene algebras on generators X is the family of regular subsets. And this is the free delta algebra for delta, the set of regular coterms defined by finite systems of linear affine equations of this form. So these are linear equations, linear affine equations where the A's are and the B's are constants and the X are variables. You give me a finite system and you can unwrap that into a giant, you can unwrap any system like this into a giant coterm. Give me any system, I'll give you, in fact, I'll give you n coterms that are obtained by unwrapping these axioms, these equations. And take the set of all of those things, those specify completeness conditions, and those suprema all have to exist. So that's the syntactic expression of the completeness conditions required for star continuity in semi-rings.
By unwrapping
Yes.
here, you mean you substitute the expression for x1, let's say, everywhere for x1 in the system of equations,
just keep substituting and substituting and substituting forever, and you'll get an infinite coterm. Right?
Okay.
And take all those, take any system like this, and take the coterms that are represented by that system. That's a big infinite syntactic thing. That is, that set of those things forms a monad under substitution. So that's the delta. And that's the continuity condition specified by the star continuity condition. Okay, here's a special case. The star continuity condition itself is generated by this infinite coterm obtained by unwrapping this thing here. Special case corresponding to this system with X and Y. Okay, context-free languages are the least solutions of finite systems of algebraic fixed point equations of this form, where F is, this is from, this is a finite term in the language of idempotent semi-rings. And these systems are essentially context-free grammars. So for example, this a to the n, b to the n is the least solution of this equation. And these equations are essentially just context-free grammars. So, but you can think of them as equations interpreted in the semi-ring of languages. And this is the least
of representing the context-free grammar as a sequence of equations, or something else is happening?
Yeah, so for, yes, any context-free grammar represents an equation. The productions of a context-free grammar represent an equation over the language of, over the semi-ring of languages.
Yeah, and if you have more than one non-terminal, you will have several equations.
Yeah, exactly. You'll have a system like this.
Okay.
So any system like this in the language of, over the language of idempotent semi-rings gives you a completeness condition which gives you the context-free languages. So the context-free languages satisfy, and there's also an axiomatization for context-free languages corresponding to the star continuity condition. It's this so-called mu continuity axiom. Okay. Here's some other examples. The OI macro languages, these are really fun. The OI macro languages and the so-called index languages. These are two different formalizations of the same thing that were studied by Fisher and Aho back in the 70s. They were used to capture some syntactic properties of programming languages that context-free grammars are not strong enough to capture. For example, that a variable may only appear in the scope of its declaration. That can't be expressed by context-free languages, but it can be expressed by these OI macro languages. So that was the motivation for inventing these things. I'll show you how it works. So productions are of this form where you label non-terminals and right-hand sides of productions with a stack, sigma. And the productions can be of the form where you can take any step without doing anything to the stack, or you can add a symbol to the stack, or you can take a symbol away from the stack. So in this formalism, you can generate some non-context-free languages. So for example, here's your favorite non-context-free language, A to the n, B to the n, C to the n. That's generated by this index grammar, or by this index grammar. So from the start symbol S, I can repeatedly add a symbol F to the stack if I like, or I can go A and duplicate the stack with A, B, and C. And then from A, B, and C, I pop the symbols off the stack and generate a string. For every symbol I pop off, I generate a string A or B or C. And then when the stack becomes empty, I go to the null string. So then A to the n, B to the n, C to the n is generated by this grammar, because I start from the start symbol, put n f's on, and then I go here and then take the n f's off and generate A to the n, B to the n, C to the n with these productions. A to the 2 to the n is another non-context-free language. It's generated by this. I can put n f's onto the stack, or go to t, and then from t, I take f off and then double the thing every time. And then finally, when I get the stacks become empty, I just generate a simple A. Okay. And this is also the same as the strings generated by these macro grammars. I have parameters. So I can have parameters. So S goes to F with epsilon, epsilon, epsilon. And if I can get X, Y, Z, I can get AX, BY, and CZ. Or then I can just take F and give it my arguments. F, X, Y, Z can go to X, Y, Z. So I can generate A to the n, B to the n, C to the n that way. And here's the index grammar or the OI macro grammar that generates A to the 2 to the n. So these are how you get terms like this. Okay, so these are the terms that come out of those grammars, and they form a monad, a delta, and gives you a monad of OI macro grammars, which is a restricted completeness property. Other examples: context-free languages, context-free languages when are frontiers of a parse tree whose paths are in a regular language. You get an index language as a frontier of a parse tree whose paths are a context-free language. And you can iterate this and get a whole hierarchy of higher order recursion, things that are used in higher order recursion. And these are all examples of what I'm talking about. They're all submonads of the coterm monad. I have a couple other examples in the paper that I won't go into: iteration theories, which was one of the main motivations, and the category of signatures. So these are all very interesting applications that I don't have time to go into. All right, in conclusion, I've got a syntactic characterization of free algebras with algebras with restricted completeness and continuity properties based on submonads of the monad as sigma coterms. Gives me a syntactic treatment of the notion of completion by omega ideals. And there are lots of questions about decision procedures, deductive systems, higher cardinalities. I don't know. There's a lot of things you can think about here, a lot of interesting stuff. And with that, I'll say thanks and take any questions you might have.
Yeah, thank you very much. Yeah, very interesting talk.
Thanks, you're welcome.
Okay, so anyone? I have some questions, but I would like people from the audience first to ask their questions.
I have a small comment.
Yes.
Many thanks for your talk. That was quite curious and interesting.
Thank you.
Could you return to the slide with the main results, please? Oh, thank you. As far as I understood, this is a sort of representation theorem, and
yes,
the construction you described is fairly similar to a sort of canonical extension. Well, my comment, perhaps there is a more general theory about the questions of representability of omega algebras or Kleene-like algebras. I don't know. I've never met such works about that, perhaps.
So the only thing I know about representation of Kleene algebras, so yes, I think you're absolutely right. There are very interesting questions there. There are some results on representation of Kleene algebras by relation algebras, concrete representation. I think the theory is not very well developed, and I think that I know some results on Kleene algebras, but it's not as nice as you'd like it to be in some sense, in that there are certain restrictions that you have to impose in order to get representation. I'm not sure about the general case for delta ideals, but as far as I know, it's wide open. Very interesting question.
Well, I had some thoughts about that in the case of residuated Kleene lattices. Well, one may consider a Kleene residuated lattice as a bounded lattice expansion. Well, a bounded lattice with operators, and as I believe, the variety of all Kleene residuated lattices non-canonical one. So a Kleene star encodes a sort of induction. So perhaps the canonicity may fail. Well, I don't know whether my thought makes sense or not.
Oh, I think it makes great sense. So I think what you may be thinking about is whether you could take say representation results of Kleene algebras or representation results of residuated Kleene algebras or Lambert calculus, something like that, and get a general representation theorem based on sort of these general conceits that I'm talking about here. Monads, submonads of a coterm monad, something like that, and get a very general approach to those types of results for which all of the specific results for specific algebras would be special cases. That's a very interesting avenue to explore, I would say. And I don't have much to say about it myself, but there's certainly lots of things in the literature that might be appropriate for starting from.
Oh, all right. Thank you.
Yeah, you're welcome.
Okay, anyone else? Any other questions?
We also have not a question, but more of a comment on that.
Mm-hmm.
So, as you see in the these coterms which are used for star continuous linear algebras. So this is a specific delta where you have these regular trees with these backtracks.
Yes.
I think this one, for example.
Yep.
And this, I think, shares much with the circular proofs, which can be used for axiomatizing various logics with fixed points and inductive style reasoning and stuff like that. I think also.
I agree. I think that's certainly true.
Yes, but here everything goes quite smoothly, meaning that you just take the standard notion of a coterm and just carve out the class of regular coterms in the sense of just well, looped by backtracks, and that's it, and it does the job perfectly. But if you try to axiomatize the equational theory of star continuous linear algebras, well, which is the same as all linear algebras, of course, then
no, that's not true.
the equational theory.
Oh, the equational theory is true.
Oh, yeah,
I'm sorry. You said the equational theory. I thought you meant the class of algebras.
No, the equational theory.
Oh, yes, you're correct. That is true. The equational theory is the same, right?
Yeah. So this is the semantic side. On the semantic side, you have these very nice coterms, which are just regularized in the sense that you have backtracks. And on the proof theoretic side, when you want to axiomatize, well, the easiest thing, the equational theory. Well, there is a work by, I think, Anupam Das and Damian Pus, who axiomatized the equational theory of linear algebras using circular proofs. But yes, their work is, so it's quite involved. So the, say, natural way of doing it fails. So it fails to be complete, to be cut free and stuff like that. And they have to do something strange. They have to introduce some hypersequential calculi. Well, everything works out, but not easily. And so this sort of discrepancy, it's something which a bit bothered me about that. I don't know how to maybe philosophically understand this.
Right. So you're talking about generally about co-equational proof systems or co-inductive proof systems.
Yeah, co-inductive, yeah. But so they, you can say that there are, well, co-inductive or non-well-founded proof systems.
Non-well-founded proof systems,
which of course will give you the equational theory for star continuous linear algebras.
Right.
And this will do even for, say, residuated cases where you don't have completeness.
Right.
Stepan, the proof systems that you are referring to, so the notion of proof is non-well-founded, or let's say similar to coterm or cyclic proofs. But the formulas, the sequence are built from are just ordinary formulas. They are not let's say such
they're
infinite
terms. They're not coterms.
They're not coterms. So it's like the non-standard part of that proof system is really in the proof system, not in the on the level of terms, on the level of formulas. Yeah. Mm-hmm.
Yeah. So,
is there such a thing? Is there such a thing as a proof system for coterms or co-formulas, objects like that look similar to these infinite terms?
For co-terms.
Yeah.
Don't know of such a thing.
Yeah.
It should be also infinitary in a sense, I think.
Mm-hmm.
But my comment was a bit different. So we consider proofs for the equational theory for terms, but the proofs are in a sense co-proofs. So they're infinite. Yeah. They allow infinite development. And from these proofs, we can actually consider only regulars. In a sense, a regular subclass of proofs, it is sufficient. But on the other side, you have to modify the sequential language to obtain this. So this is something happening there. Maybe it's only connected to cut elimination issues. Because if you allow cut, it's all natural also.
So can you give the proofs in such non-well-founded proof systems a kind of overall structure of something like this star continuous clean algebra, or some kind of structure of similar to algebras we have here? Yeah,
that's an interesting. I don't know. I don't know.
It's a question for.
Yeah, it's a question for the future, right?
I don't know.
Yeah.
So well.
I had something in a totally different direction at the beginning of your talk. So your construction started with this, let's say, the simplest case of free ordered algebra.
Yeah.
The ordering is sort of very weak. So you just compare terms by deleting certain parts of them.
Right, right. So the ordering is very simple on the terms and on the coterms.
Yeah. So it is characteristic to all the examples that appear here, right? So the ordering is that ordering, and then the objects themselves, they grow in complexity, but what becomes of this approach if you start with some other natural ordering or terms?
Well, so there's one simple step you can take, simple generalization, and that is to allow contravariance. So allow a function symbol to be contravariant in some argument instead of covariant, which means if A is less than or equal to B, then f of A will be greater than or equal to f of B. And that's useful in type systems. So for example, the functional, the function, so in recursive types, for example, a recursive type is a coterm. And the function constructor, the arrow constructor for function types, is covariant in the range and contravariant in the domain. So if you have a notion of subtypes, which is an ordering, if you have f, so the way it works is, let me stop sharing here for a moment and get something else going. I'll show you what my system looks like for my lectures.
By the way, if you want to write on the okay.
This is my system for lecturing these days.
Okay.
So if you have sigma prime less than or equal to sigma, and tau less than or equal to tau prime, then you can conclude that sigma arrow tau, this might be the wrong direction.
No, this is greater or equal.
I'm sorry?
I think it should be greater or equal, because contravariant on the first one. Okay, you didn't.
Yeah, I'm putting the. Okay, so if I have something that can take a sigma, then it can take, and if tau, so it's covariant. So if tau is a subset of tau prime, then it's covariant in the range, but contravariant in the.
No. This prime should be on the left, I think. No, it's okay. Yeah, it is out.
It's okay.
Yeah, I think this is right, because sigma prime less than or equal to sigma prime less than or equal to sigma. Okay, so you can see that this arrow constructor is contravariant in its first and covariant in its second. So if there's a very simple generalization you can make that would be useful. But I mean, we didn't do that, but one might consider doing that. And then you wouldn't get you of course would get a much more complicated definition of what it means for one coterm to be less than another coterm. You'd have to prove that, you'd have to establish that inductively, because I think, so right now with all covariants, a term S is less than or equal to term T if S can be obtained from T by just deleting stuff.
Mm-hmm.
But I think I think what you have to do is look at the path that goes down to the thing you deleted. And if you go through and if you go left an even number of times, then it's covariant. And if you go left an odd number of times, then it's contravariant or something like that. So there's some complicated algorithm you have to perform in order to determine when one coterm is less than or equal to another coterm.
Okay.
I have a remark on this.
Yes.
Not well-founded proof systems for not well-founded terms. In the context of the Gödel probability logic, one can consider non-well-founded formulas or non-well-founded terms such that any infinite branch you need contains infinitely many applications of the model connective, of model connectives. And for such non-well-founded formulas or terms, we can consider Kripke semantics, neighborhood semantics, that is over any algebra of subsets of a Kripke frame, GL Kripke frame, Gödel Kripke frame. One can uniquely define valuations for such non-well-founded formulas, and that seems that non-well-founded sequent calculus for the Gödel probability logic will be complete if we consider non-well-founded formulas in this sequence, if we allow non-well-founded formulas in this sequence. So the situation in GL.
Okay. That may be the only example that we have of that kind, right? Okay.
I have a time constraint. I have office hours at 1 o'clock. Zoom office hours at 1 o'clock. So I'm going to have to sign off before then, but we have another 10 minutes or so if you have more to discuss.
We will be then fast. So if anyone has some really urgent question, then please ask. Otherwise, we will thank our speaker. Yeah. Yes, Max. Max?
Yeah, I'll say only our big thanks.
Okay. That was not a question, but I think everybody shares the same feeling. Thank you very much.
Well, thank you. It was a pleasure. I think it went okay. You think that this was?
It was very.
This is not so bad. This is not so bad.
The connection was perfect, better than in other cases that we had.
Yeah, I'm
due to very advanced technology on your side, so you have a good internet connection at home that must have helped.
I have a very nice connection, and for which I'm very grateful. Yeah.
Okay. Thank you very much.
Okay. Thanks so much. Goodbye, everyone. It was a pleasure.
Yeah.
Stay in touch.
Goodbye. Thank you.
Bye.
Have a nice day.
Thank you.